to be used in high performance.
Can you guys see this?
All
right, I am going to be reading kind of from the script.
Do you want to hold the camera or something?
Yeah, do whatever you need.
Do you want?
I don't have the camera.
Okay, thank you guys so much for coming. I hope that, I love physics and I love theoretical physics, but oftentimes I feel like it just kind of goes like this. You know what I mean? But I wanted to try to explain it in a way that people could understand and that would capture some excitement. And so this is my attempt to do that. I hope it works. Okay, so as technology and science continue to spearhead revolutions in contemporary society, science fiction's popularity has been increasing. For example, between 2010 and 2019, 7 of the highest grossing yearly films had sci-fi elements, as compared to 2 from 2000 to 2009. So to create more plausible or interesting stories, as we all know, sci-fi often draws from modern science. It draws ideas from it. And one idea that's really popular right now is the multiverse. So just to give you some examples of where the multiverse crops up. Spider-Man, Into the Spider-Verse, okay? A bunch of multiverses, or parallel worlds. Parallel worlds in the movie that's in theaters right now, Everything Everywhere All at Once. Multiverse of Madness, need I say more? Stranger Things with the Upside Down. There's tons of other examples. But anyway, it's clear that Hollywood's kind of obsessed with the multiverse right now. But what is the multiverse? So while many theory... Whoa, sorry. I kind of went off script for a second. Okay, I just want to talk a little bit about the science behind the multiverse. So there are a lot of different theories that result in an idea of parallel universes or multiverses. I'm going to focus on, I planned for 3, I'm actually going to focus on 2. The many worlds interpretation of quantum mechanics and eternal cosmological inflation. Those are 2 ideas in which a multiverse comes about. String theory compactification in the landscape of vacuum, I'm not going to focus on that because I didn't have time. So, and I think that these other 2 topics will be enough. Anyway, so digging into these theories is not going to be as visually exciting as watching people jump into portals and stuff like that. But can I just keep in mind here, this is real, okay? These are real ideas about real life. So let that kind of drive you. Okay, so we're going to talk about the multiverse.
Let it be your chauffeur.
So here's an example of where this crops up in Stranger Things, season 1. If anyone's seen this.
TV remote.
Basically, there are parallel universes, which is how long, which is infinite variations of it. Which means there's a world out there when I was trying stuff.
Yeah, that's not what we're talking about.
Anyway. Yeah, okay, so it crops up in Stranger Things, the interpretation of quantum mechanics known as many worlds. So, but in order to kind of understand the many worlds interpretation, we're going to have to do a little bit of basic concepts in quantum mechanics. So quantum mechanics is just a physical theory for describing things that are very small. For example, at very small scales, there are some properties of particles, such as energy and momentum, that become quantized when these particles are bound by other forces. So, for example, in the hydrogen atom, you have an electron which is bound by a proton, and because of the binding of the proton, the energy and angular momentum of the electron becomes quantized. So it can only exist in certain states. It can't exist between them. Okay, a second thing that happens is that fundamental objects, such as electrons, exhibit both wave and particle-like properties. You've probably heard of particle-wave duality before. And we'll get to that. And 3, the results of measurements appear to be intrinsically probabilistic, okay? In the sense that there's probability not because we just don't know everything, but because nature itself kind of has a bit of randomness or statistical like variation in it. So, to demonstrate wave-particle duality, we are going to watch this video. And this video is going to be important, and yeah, it's going to be important to kind of the problem that ends up resulting in different interpretations of quantum mechanics, such as the many worlds. Okay, so this is the two-slit experiment. You may have heard of it before. If you just send basic particles through it, it's going to do that, okay? It's just going to bounce. It's going to have, you're going to see something on some slit behind it. That's what you're going to observe. Okay, now let's say you're sending like water, okay, through two slits. What's going to happen? It's going to create wave patterns, and they're going to be peaks and troughs. Okay, and so it's going to create a pattern like this on the maybe observation like wall. Okay, now let's say that you have a quantum object. It exhibits particle wave duality. Okay, it acts like it goes through like a wave, but you only observe one particle. So what's going on? Well, if you have the wave, if you have particles continue to shoot like electrons or something like that, then you're going to get a statistical distribution that looks like it's from a wave pattern, even though you're only shooting one particle at a time. But if you try to observe it, you break the pattern. Okay, if you try to look to see which slit the particle's going through, the wave nature stops. Or rather, it stops in that moment. Hey! Hey! Okay. Did you catch that? Okay, so there's something weird. Let's go to this. There's something weird going on with when you look, okay? It acts like a wave, and then when you look at it, it becomes a particle, and when you stop looking, it becomes a wave again. Did you see that? Okay, that's really weird. Why should that happen? Okay, that is the question that has like scientists flummoxed. And it's the question, among other questions, that results in multiple interpretations of quantum mechanics. So there are lots of interpretations. By far, the most popular interpretation is the Copenhagen interpretation, which was pioneered by Niels Bohr and Werner Heisenberg. And in the Copenhagen interpretation, you have this wave function, okay, the kind of wave-like nature of particles. And what happens is that this wave tends to evolve, but what the amplitude of the wave represents is it's proportional to the probability of measuring the particle to be in that position. So once I measure the particle, it collapses, okay? The wave function collapses, and I measure it at a point, and then when I stop observing it, it continues to evolve like a wave function. Okay, so that is the Copenhagen interpretation of quantum mechanics. But today, we're going to be focusing on another interpretation, known as the many worlds interpretation, which was proposed by Hugh Everett as teacher, whatever his name is, in Stranger Things was talking about. Okay, so in the many worlds interpretation of quantum mechanics, the entire universe is described by one large wave function, okay? This actually isn't really controversial, nor is it unique to Hugh Everett's theory. It's basically equivalent to saying that no physical system can be completely cut off from the outside world, okay? That there's no such thing as a completely isolated system. Or, to paraphrase John Donne, no quantum system is an island. Anyway, so, however, Everett begins here because he wants to emphasize what's going to become a critical point. We, the observers, are also quantum systems. We, the observers, and the thing we're observing are actually just part of the same quantum system, okay? and that's going to affect how Everett explains quantum measurement, or the problem associated with measurement. So, in order to explain measurement, we're going to use the thought experiment known as Schrodinger's cat. Okay, so this actually was proposed by Erwin Schrödinger, who was at the basis of quantum theory because he disliked some of the implications very much. And so you have a cat in a box, and you have a radioactive material, poison, a hammer, and a Geiger counter. Okay, if this radioactive material, such as uranium, decays and the Geiger counter detects it, or then the Geiger counter will detect it, we'll assume that it's a perfect Geiger counter, in which case it's going to trigger the hammer to break the poison to kill the cat. Okay? But a principle of quantum mechanics is known as superposition, which is just like the superposition of waves. You know how you can have a wave that goes like this, and then you have a wave that has the opposite amplitude, and then you add them together and they cancel out. Okay, that is something in quantum mechanics that's verified. The whole double slit experiment, that shows that superposition works. Okay, according to superposition, the radioactive material can be in both an excited and an emitted state at the same time. Basically, it can be in a not decayed and in a decayed state at the same time until something measures it. So basically, until the observer opens the box, the cat is both dead and alive at the same time. That flies in the face of reason. Okay, that seems totally ridiculous. Also, you end up having a lot of questions about what a measurement is. It really kind of shows why the idea of measurement is so weird. Is the person the one capable of making a measurement? Can the cat make a measurement? Can the Geiger counter make a measurement? Is consciousness required to make a measurement? What's the problem with measurement? Why is this weird stuff happening? Okay, so that is an example of a problem in the Copenhagen interpretation of quantum mechanics, and I'm sure that the people have some answer to it, but we're not going to focus on it. Because we want to focus on what Everett says. Okay, so Everett interprets this idea the following way. In reality, he says, there's no such thing as measurement. Because we're actually just all part of the same quantum system, the same universal wave function. Okay? So instead, when an observer interacts with the box, their quantum system becomes correlated with the cat's quantum system. In other words, the superposition of dead and alive that the cat is in remains. But now, there's also a superposition of you in the observed dead and observed alive state. Okay? Since an observer's reaction is dependent upon the cat's state, the observer also exists in a superposition of states. These two outcomes evolve independently. The pattern of superposition and coupling applies to any event in general. All possible outcomes happen where each outcome is an independent branch or reality in the universal wave function. Since each branch is self-consistent, in each reality there's no logical discrepancy. So, for example, if you think about your past, everything makes sense because it's all part of the same branch. So, in this view, it's like we exist at the end of each branch of lightning. Okay? The many worlds exist simultaneously, and So so you're like the end of each branch, okay? And every event causes a branch to come off. And in this view, every version of you that the laws of physics allows exists. So you're the judge, you're the lawyer, you're the president, you're the vice president, you're the fashion model, you're the singer, you're the author, you're the scientist. Every possible you that could be is out there somewhere. Okay? Now, there are arguments against this interpretation of quantum mechanics. For example, a frequent complaint is that the many worlds interpretation is non-falsifiable. That is, there's no way to find out if the theory is true or not. Whether it's true or not, you're going to experience your life the same way. That's a problem. Another argument is over how the many worlds interpretation explains our perception of probabilistic results. So if all outcomes in any event do happen, how do you describe the idea that we experience a most likely outcome? Something that is overwhelmingly more likely to happen than some other And so those are some problems with many worlds. Nevertheless, the theory remains attractive because it does away with clumsy ad hoc descriptions of wave function collapse and other behaviors that seem unfamiliar and illogical. Okay, that was the many worlds interpretation of quantum mechanics.
Mm-hmm.
Now let's talk about another idea which leads to multiverses, which is eternal cosmological inflation. This one is going to get a little bit more abstract,
Nice.
just so you know.
Picasso, I like it.
If the first one didn't feel abstract enough. Okay, to understand this theory, we're going to need to go back in time. In the early 1900s, astronomers Henrietta Swan Leavitt and Edwin Hubble made some crucial discoveries. So Leavitt discovered that a relationship between the period and brightness of these stars called Cepheid variables, and doing so allowed us to calculate the distance to objects in space, faraway objects. Now, Edwin Hubble, he used this to calculate the distance to the Great Andromeda Nebula, finding out that the Great Andromeda Nebula is not a nebula, but is actually 2 million light years away and is another galaxy. So this opened up the idea that there are other galaxies besides our own. Furthermore, as he looked at the distance between galaxies, he noticed that the light from other galaxies were redshifted according to how far away they were. So let's give an example of what redshift is. Okay, redshift, so this is a star, okay? And we're just gonna imagine the star sitting in place. It looks yellow. Now, when this star starts to move toward us, it's going to be shifted towards the blue end of the spectrum, and when it moves away from us, its light will be shifted towards the red end of the spectrum. This is going to keep going, so I'm going to stop at actually, whoops. Yeah, let's, anyway, so that's the idea of redshift. And so if you see the galaxies away from us are redshifted, that means that they are going further apart. It means that the universe is expanding. So the realization that the universe is expanding led to the modern theory of the universe, which is now known as the Big Bang. And we've all heard about that. The universe started as a tiny little speck and then went boom. Okay? And that it's still going boom. Okay, so scientists continued to, I'll explain this picture right now. This is our universe in like log scale, if you know what I mean. Okay,
Mm-hmm.
so yeah, this is our universe in log scale. Okay, obviously, I mean it's really silly, but it'll get the point across. Anyway, so
Yeah.
scientists continued developing the Big Bang model over many decades, but as they did, they ran into some conundrums. One problem is known as the horizon problem. That's why I have this picture here. So the horizon problem requires knowing three things: the size of the universe, the age of the universe, and the homogeneity or uniformity of the universe. So, as it turns out, the universe is really uniform. No matter what direction you look in, space is distributed in pretty much the same way. This implies that the universe is in a kind of equilibrium state, just like the molecules of gas in this room are spread out evenly, so is our universe. Because, right, the gas in this room has had enough time to kind of get to the same state. Everything around here looks basically the same. If you're
There's no suffocation hole.
Yeah, exactly. There's no spot where there's just like no air. That would be really weird. Okay.
Eyes bulge.
But it's really weird that our universe is like this. It's weird that it's the same everywhere. It shouldn't be. Here's why. The observable universe is 93 billion light years across. Okay?
Yeah.
It's 93 billion light years across. The edge of the observable universe is actually when, past that point, things are, like, due to the expansion rate of the universe, things past here are moving away from us faster than light, and so we can't see them. Now, I say moving, really it's the universe is expanding, it's not like things are moving. Nevertheless, because light is limited to the speed of light, we can't see that stuff. Therefore, we're causally disconnected, because no information can travel faster than light. Now, if the universe is 93 billion years across, light years across, but only 13.8 billion years old, that's a problem. Because that means that stuff on this side of the universe could not have communicated with stuff on the other side. So it has no right looking the same as stuff on the other side of the universe. Do you see what I mean?
Yeah.
It's like if
Yeah.
it's like if you pop a balloon in a vacuum of this huge room, and then like you pause it like 1 microsecond, and as it turns out, like the gas is like evenly distributed in like the Walmart supercenter. You know what I mean? That has been like evacuated of all air except for that balloon. You know what I mean? That's really weird. So what's going on here? What's going on? Another problem concerns the universe's shape. Okay, this is another problem with the Big Bang model. Okay, the universe actually has curvature. Space-time has curvature. This is the 2D representation. Our universe is 4D, according to the most accepted theories. Okay, but let's not worry about that right now. Okay, if the universe had enough stuff packed into it, or enough energy density, then omega as greater than 1 would cause the universe to curve like the top shape, where 2 beams of light that are emitted from the same point could converge back onto the same point eventually. So in such a universe, a telescope could look out to the edge of everything if it were powerful enough, and it could see its own planet. That's that universe, okay?
Science.
We're not, believe it or not, we're not in that universe. Okay. In this universe, there's not enough energy
Explain
density,
mirrors.
and 2 parallel light beams would diverge, okay? They keep diverging. That's this universe. We're in this universe where 2 parallel lines, beams of light, stay together, okay? The universe is flat. The universe is flat. And this is really weird. You know why it's really weird? It's weird because the curvature of the universe is analogous to like a ball sitting on top of a hill. Okay? Where the top of the hill means the universe is flat. If the ball rolls one way, then it has positive curvature, and that positive curvature will keep going. You know what I mean? It's like curvature begets curvature. Okay? And if it rolls back the other way, it'll have negative curvature, but also that curvature will beget more negative curvature. And the universe is 13.8 billion years old. So over 13.8 billion years, this ball has stayed on the top of the hill. Okay? That we've calculated that requires the universe in the beginning to need to have been like smooth. This thing to have been like equal to 1 part in 10 to the 62nd power. Okay? That's some nuts up. Like, it has to be perched perfectly on top of that hill. Okay? And so these are some problems. There are other problems, but these are 2 of the really big problems with the Big Bang model. Okay? Now, in 1979, a guy whose name that I failed to write here and forgot, proposed, Alan Guth is his name. Anyways, he proposed a model which solved these problems. It's known as cosmological inflation. Okay, this is a depiction of our current model of the universe's expansion, and it illustrates the mechanism of inflation. So, in the beginning, some event triggered the universe's expansion. You can ask me questions about that later. There's some
The Bible
technicalities
explains
there.
it clearly.
This expansion was quick by our standards, but not quick enough to account for some of the problems that we just talked about. Now, imagine that there's a field throughout the universe called the inflaton field, okay?
Ooh.
Like a temperature map, this field has a value everywhere in space. And just like a temperature map, once again, it likes to reach a state in which every point has the same value. Okay, we're going to call this an equilibrium state. Now, just like temperature, this inflaton field and other fields, by the way, can have more than one equilibrium state, right? So like if all of the temperature is like 100 degrees, if all of it is 200 degrees, right? Those are equilibrium states, right? Without getting too detailed. But like, the quantum field, such as the inflaton field, can have multiple different equilibrium states. However, the most stable state, the state at which the inflaton field has like a value of 0 everywhere, is known as the vacuum state. Okay, now let's imagine that the universe is filled, or that this little patch right here is filled with an inflaton field in false vacuum. That is, it's in equilibrium, but it's not at the ground state. It's not at the 0 state. This homogeneous energy in the inflaton field drives the universe's expansion due to stuff in general relativity, which I'm not going to get into because I don't know. But it has to do with differential geometry. Anyway, so
I like your other geometry.
So the inflaton field's energy, which is homogeneous everywhere but non-zero, is going to drive the universe to expand at an exponential rate. And as this occurs, inhomogeneities are smoothed out. So consider, for example, even if you have a rough surface, if you hone in small enough, things might appear smooth on a small scale. Now, consider that now this is a subatomic scale, and so just consider that any variations in density or temperature in this early universe would be spread out after inflation over at least 10 to the 26 times their original length. Okay, so with this kind of stretching, regions that were once very close and hence looked very similar are stretched to impossible distances and become causally disconnected. This solves the horizon problem, because regions that are causally disconnected today weren't causally disconnected before inflation, and they equilibrated at that point. This also solves the problem of flatness. Since the original patch's energy density, like the inflaton field energy density, would soon become the only energy density that mattered as inflation spread. And since it was uniform, therefore the energy density throughout our little patch that inflated was uniform, and so the universe would be smooth and flat. Now, as an aside, I just had to put this here. If anyone has seen this, this is the cosmic microwave background, or the CMB. Cosmological inflation explains why the CMB looks the way it does. So the CMB, just to let you know, it's an imprint of light, okay, at its earliest observable point, some 400,000 years after the Big Bang happened. These color variations are a temperature map, an actual temperature map, not like the temperature map analogy I was using. It's a real temperature map. And basically this has the same temperature, but there are tiny, tiny fluctuations in temperature here, which we color, hot or cold. Now, these temperature fluctuations are believed to have happened because of quantum fluctuations in the value of the inflaton field when inflation happened. Okay, so inflation explains why this looks the way it does. Okay, let's go back to the other picture. As this model shows, many scientists believe that after a short period of rapid expansion, the inflaton field decayed to its true vacuum state, and inflation ended. But some physicists argue otherwise. Some physicists argue that there's no reason for the inflaton field to have stopped expanding, other than that we observe that the universe is not expanding like crazy. But some believe that inflation continues unabated, and that pockets of space-time, like our own universe, are just regions where inflation has stopped, because in this region, inflation just dropped to its vacuum state. Okay? So, in this idea, there's kind of a constant rhythm of expansion as the inflaton field just keeps expanding space-time. And there would be an ever-increasing number of kind of bubbles, like our universe, where inflation stopped because inflation just kind of dropped from its false vacuum, where it's equilibrium but not vacuum state, into its true vacuum, where the value is 0. So, each of these bubbles, where inflation had subsided, would be causally disconnected, so no information could pass between them. Some believe that each bubble independently goes through a process known as spontaneous symmetry breaking. What that basically means is that the fundamental constants of nature in each bubble would be different. Thus, as inflation continues, an infinite number of universes are born with randomly selected fundamental constants. So each universe would have its own set of physics and evolve according to them. Do some of them create the conditions for life? Are copies of you or something like you in some of these infinite universes? It's just really a numbers game, and as they say, the possibilities are literally endless. So, yeah, it was pretty cheesy.
Nice. We go.
Anyway, but that is the other idea of cosmological inflation. Thanks for letting me talk to you, and I'd love to answer any questions.